Hello my young geometers, welcome to our next lesson. This is section 11-8, Geometric Probability, and it starts on page 461 in your textbooks. Now, I'm going to be going through this section under the assumption that you already have dealt with probability in the past. So I'm only going to describe that very briefly for you, and then we're going to talk about how we can apply geometry to probability, or probability to geometry, whichever way you want to think about it. So, probability is often thought of as your chance of something happening. So if I have a coin that one side is heads, the other side is tails, and I flip that coin, I'm going to have a 50% chance, or a 1 out of 2 chance of getting heads, or a 1 out of 2 chance of getting tails, depending on which one I want it to be. Likewise, you can think in terms of a deck of playing cards. The chance that you draw a red card would be a 50% chance, because there are 26 red and 26 black cards in your typical 52 card deck. You could also think in terms of pulling any individual number, like your chance of pulling an 8 would be 1 in 13, because there are 13 different values that the card could have, 2 through 10, and then 4 face cards. So it would be a 1 in 13 chance. You could think of your chance of pulling, like say, a ace of spades. Now there's only one of those, and there's 52 cards in the deck, so your chance of pulling an ace of spades would be 1 out of 52, and you could also calculate the percent by doing 1 divided by 52. So, going with that basic assumption that you are familiar with probability, if you're not, please let me know. We're going to be going ahead and learning about geometric probability. And there's a lot of really cool applications of geometric probability that I think you're going to enjoy some of these problems. They're almost like little puzzles. So, there's basically 2 points to geometric probability. That's kind of like linearly, like if you look in terms of a line, or if you look in terms of an area. So we have like length and area, kind of the 2 measurements we've dealt with so far in geometry. So let's say I have a length of a line, and I'm going to have points A, B, and C on it. And let's say that the length of AB is, we'll go with 5, and the length of BC is 3. And I'm going to pull at pick a point at random on here. And I want to know what are the chances that I'm going to pick a point that is in the segment AB. So I want to figure out what the chance, if I pick a point at random from here, that it'll be an AB. And as you might expect, it is going to be 5 divided by the total length. So the total length of this is 8. So my chance of picking a point here is going to be 5/8. So the generic way to write this is that I'm going to do it exactly the way the book has it. If you have point A, you have point C, and you have point B. If you pick a point P at random, then the probability that that point is on the segment AC, probability that P is on segment AC is going to be the length of AC divided by the length of AB. So I'll just write AC over AB. Make sure you guys can see that. So that's going to be your probability that it is on that segment. It's just going to be the length of that segment divided by the total possible number of things that you could pick. So the total length. Okay, the way of doing this for area is going to be very similar. So let's say that I have, a rectangle, and I have some area here that has an area of 4, and let's say the area of the entire rectangle is 12. Then my chance, if I pick a point at random from this rectangle, the chance that it is going to be in that little rectangle of 4 is going to be 4 out of 12. Which reduces to 1/3, or about 33%. So, to put it in a more generic way, I'm going to do it the way your book has it. We have some area, and this area is S, and we have another area of R. The chance that if we pick a point P at random out of this region S, the probability that it is going to be in region R is going to be the area of R divided by the area of S. So that's the chance that P would be in that region R. And you can kind of think of it, imagine that this is like a picture from the sky. You're dropping marbles out of an airplane or something, and they're going to come down and randomly hit in this area. We're guaranteed it will be in this area. The more area there is in S, the less of a chance that it's going to land in R. But if we assume that they fall just about evenly, they're evenly distributed, then we will see that it would correlate to their areas as to how often it actually lands within that area. So hopefully that is making sense. And so what I'm going to do now is I'm actually just going to work through the examples that your book gives in this section, because I think they're very good and creative applications of this geometric probability to real-world situations. So let's go ahead and start with example 1 in your textbooks. And this is on page 461 again. So this is actually relating it to a bus stop, which is kind of funny. It's using geometry to think about time. So you're like using space to visualize what time works like. And I think that's pretty cool. But basically it says that every 10 minutes the bus is pulling up to this bus stop, and it waits for 2 minutes before leaving. So like the thought is like, what's the chance that if you just show up to this bus stop at a random time, the bus is going to be there? So it waits there 2 minutes, and it comes every 10 minutes. And there's a nice little drawing on the page 461, and it's a little timeline. So this is using kind of the line way of thinking about geometric probability. So let's say that this is 0 minutes, and the bus has just arrived. It is going to wait 2 minutes, and then it's going to leave. And then we're going to have, let's see, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here it is, 10 minutes. It is going to arrive at that 10-minute mark, and then wait 2 minutes, and then leave. Then 3, 4, 5, 6, 7, 8, 9. 10 minutes later, it shows up again, waits for 2 minutes, and then it'll leave. 2, 3. And so on. So the way that they visualize this is they actually kind of color in the segments that the bus is there. So you can think of this bus as being there, then, and you can start to see that 2 minutes out of every 10 minutes is blue. So if you pick if this is going on all day long and you just pick a random spot on here, the chance that you are going to come at a time that the bus is there waiting is going to be 2 out of 10, because this length is 2 right here, and this whole length is 10, and this just gets repeated over and over and over again. So we can really just think about one 10-minute segment, because you're gonna come during one of these segments. The chance that it is going to be there is going to be 2 out of 10, or 20%, or 1/5. Any of those ways would be an appropriate way to write it. So this is a really neat way to think about time in terms of like a timeline. Geometry can apply to things that aren't even in space. This is time, which is a little bit different. Okay, so that is one application of geometric probability. The second one is probably more what you think of when you think of geometric probability, like a probability that something is going to be in a specific area. And they use a bullseye to demonstrate this. So they have 3 concentric circles making up a target, and they say you have some beginner archer shooting at this. And if the beginner archer is shooting at this, it's going to be completely random when it hits. So they want to get the bullseye, but they don't have aim yet, so it's just going to be hitting completely randomly. The arrows are going to be evenly distributed across this area. And note that is a key, because if this was an Olympic archer, then it would not be evenly distributed. He'd be landing in the bullseye just about every time. So in order for probability to work, you need randomness. If you don't have randomness or even distribution, then geometric probability falls apart and you can't use it. But you can use it in a case like this. So the radius of the inside circle is 1, radius of the outside circle is 2, or the middle circle I mean, and then the outside circle is 3. So we have these 3 different lengths for the radii of these 3 concentric circles. So what the question is asking is, what are the chances that the archer is going to get it in the bullseye, so in this middle circle here, which in the diagram on the book it's red. We don't have red right now. And the chance of that is it's just going to be the area of this inner circle divided by the area of the whole circle. So the area of the inner circle is pi r squared. R is 1, so it's going to be pi times 1 squared. And we're going to divide that by the area of the entire region, which is pi r squared, and r is 3, so pi times 3 squared. Now note here the pi's actually will cancel out, and so you're left with a 1 out of 9 chance of hitting the bullseye completely randomly here. Now this is not in the book, but I'm going to go ahead and ask it because I think it'll help you out with thinking about this. What are the chances that it is going to hit in this middle circle but not in the center circle? I think that'll be a good question. Go ahead and pause the video and see if you can figure it out on your own first, and then I'll go over it. So the way that we're going to do this is we're going to have to look at the area of that region divided by the area of the whole region. And you might be tempted to say, okay, well it's going to be pi r squared, and r is 2, divided by pi r squared, where r is 3. So it's going to be 4 out of 9, a 4 out of 9 chance, 2 squared over 3 squared. And that is the chance that it'll get inside this circle, but that would include the bullseye as well, because the entire circle contains that bullseye. But we want to figure out only this region right here, not the bullseye. So we're going to have to subtract that area out. So it is going to be, I'll write it up here, the area of this whole center circle minus the area of that bullseye, and then divide that by the total area of the region. So we're going to have I'll do pi r squared. Pi times r squared, r is 2, so that becomes 4. So 4 pi. We're going to subtract out the center circle, which is 1 pi, because it's pi r squared. Pi times 1 squared, which is 1. So it's going to be that, and we're going to divide that by the total area. And the total area is pi r squared, where r is 3, so it's going to be pi times 3 squared, which is 9. And so then we end up with 4 pi minus 1 pi, and if you have 4 pi's and you take 1 away, you're left with 3 pi's. 3 pi's out of 9 pi's, and you can see this is actually going to simplify to 1/3. So it's going to be a 1 in 3 chance that you get it in here. And then actually with that knowledge we could go ahead and figure out what would be the chance of getting in the outer circle, but let's not worry about that right now. You can figure that out on your own time if you like. Let's go ahead with the next example, and this is going to be perhaps the one that seems trickiest to you, and it takes a little bit of thinking to get your mind around it, so if you don't understand it right away, don't give up. I am sure you'll be able to with a little bit of brain power and time. So, in this example, it's talking about a carnival game in which you toss a coin onto a grid. So I can even turn this over. You have a grid, you're tossing a coin onto it, and it's basically asking what are the chances that your coin is going to land somewhere in the grid without touching any of the lines. So say your coin is maybe this big, like right there you would win because it doesn't touch any line, but if it lands over here, it's touching lines, so you lose. So it's asking what are the chances that if you know the dimensions of the grid, or each little square of the grid, and you know the dimensions of the coin you're tossing, what are the chances that you're going to win this game? And of course, being a carnival game, it's going to be low because it's somewhat of a scam. So, let's go ahead and consider how we would go about doing this. It is telling us that the squares of the grid are 30 millimeters on each side. So we have squares with sides of 30 millimeters. And we have coins that have a radius of 9 millimeters. This is a dime. I'm not going to draw it bigger than the square. I'll make it at least somewhat to scale. So we have coins that have a radius of 9 millimeters. Now, the way that the book has you think about this, and I think this is a good way to think about it, is in order to win this game, the center of the circle has to be more than 9 millimeters away from the edges of these grid squares. And while there's going to be hundreds of squares on this board, the center of the coin is going to land in only one of those squares, so we only have to think about that square that it lands in and figure out the probability that it's going to be in the center there. So it doesn't actually matter how how big the grid is. It could be a mile long grid of these here, or this grid. Oh, hang on, lost my camera. Let me get that back. So it could be a big grid, or it could be just like a piece of notebook paper with a grid drawn on it. The chances is actually going to be the same because you just have to consider the square that the coin lands in and see whether it touches the edge or not. So let's draw the square that the coin lands in. I have it drawn above, but I'm going to draw it bigger down here so we have more room to work. Now, each of the sides of this are going to be 30 millimeters. All right. And we're going to be having our coin with a radius of 9 millimeters landing in here somewhere. And because the edge of the circle is all 9 millimeters away, if it's touching a line, the edge is going to be touching it, and so the center would be 9 millimeters or less away from the edge of the grid. So what we could do is we could think in terms of all the spaces where the center of the coin could land where it wouldn't touch any of the sides. So there's going to be this little square in the middle here, in the middle of our big square. And if our coin lands in that square, then we win because the edge is not going to touch. And that square is going to be 9 millimeters away from all the sides. So this distance right here is going to be 9. This distance right here is going to be 9. This distance here is 9. And this distance here is 9. And I could draw in the other distances as well. And this is where the diagram from your book is coming from. Now, those of you who just look at the diagram without an explanation will probably think you're looking at 9 of the grid squares from the game, but that's not actually what it's drawing. Only the black is actually the grid square. And if the center lands anywhere inside this inner square, then you win because its center is going to be more than 9 millimeters away from the edge, and with a radius of 9 millimeters, it's not going to hit the edge then. So all we have to do now is find the area of this inner square and divide that by the area of the whole square, and that'll give us our geometric probability of it landing there. So we need to find the sides of this square. We know that this whole length here is 30. We have 9 here and 9 here. So that's going to be 18 taken away, so this has to be 12 so that it still adds up to 30. So we have 9 plus 12 is 21, plus another 9 is 30. So the edges of this square on the inside are going to be 12. And so its area is 144. And that's going to be square millimeters. Now, the area of the whole square, this whole region, is going to be 30 squared, 30 times 30, which is 900. So our probability is going to be 144 divided by 900. And when you work that out, it should become about 16%, ishly, 0.16 or 16%. Or you could probably find a way to reduce that fraction nicely. And so that's going to be the chance that you win this game. So even though the coin is smaller than the grid, there's still a very low chance because there's a lot of this region here where you could end up losing the game. Now, in your homework, you're actually going to have to do this again, but with a different coin. I think you're going to have to do it with a quarter. So pay attention to this. Make sure you know how this works. I think that is all the examples that I'm going to do for this lesson right here. Please let me know if you have any questions. I know this is kind of a little bit of a different sort of geometry than what we've been dealing with, but it applies nicely to the areas that we've been talking about, so this is a good time to learn about geometric probability. When thinking about these problems, try and think creatively. Maybe think outside of the box if you need to. You can use everything else that you've known about area to figure out the areas, and basically you're just looking for the area of interest divided by the total area that you could land in. And as long as it's evenly distributed, then your geometric probability will hold. Also think in terms of lines in the same way. It's just kind of that one dimension rather than two dimensions. So I hope you enjoyed the lesson, and I will see you next time.